What if I told you that one of the smallest planets in our solar system has a tail, a glowing stream of particles stretching millions of kilometers into space? This is not science fiction. This is Mercury, and its mysterious tail may be the key to understanding not only this extreme planet, but also the hidden forces shaping our solar system. Chapter 1. The most extreme planet. If you look at the night sky, Mercury is there, shining close to the horizon, often hidden by the glare of the sun. To the naked eye, it seems like nothing more than a small star. But beneath that faint light lies one of the harshest worlds in our solar system. A planet so extreme, it almost feels alien, even though it is our closest neighbor to the sun. Mercury is the smallest planet in the solar system. It is only a little bigger than Earth's moon. Yet what it lacks in size, it makes up for in intensity. Every feature of Mercury is amplified to the extreme. Temperatures, radiation, gravity, impacts. Everything here is harsher than almost anywhere else we can imagine. Let's begin with temperature. On Earth, the hottest deserts reach around 50 degrees Celsius. On Mercury, the sun-facing side climbs to more than 430 degrees Celsius. That's hot enough to melt lead. Yet, just a short distance away, on the planet's dark side, temperatures plunge to minus 180 degrees. This brutal swing happens because Mercury has almost no atmosphere. There is no blanket of air to trap heat and spread it around. Day is scorching, night is freezing. The result is one of the largest temperature differences of any planet in the solar system. Now add radiation. Being so close to the sun, Mercury is constantly bombarded by solar particles and intense ultraviolet light. This radiation strips away atoms from its surface, eroding rocks and releasing tiny particles into space. Over billions of years, this has created a fragile layer around the planet called an exosphere, kind of ghost atmosphere, so thin that it is barely detectable. Yet it is enough to interact with sunlight and solar wind, giving Mercury some of its strangest features, including the mysterious tail we'll explore later. Then there are the impacts. Mercury has no protective atmosphere to burn up incoming rocks. Every meteor, no matter how small, crashes directly onto its surface. The result is a scarred world, covered in craters of every size. Some craters are so huge, they stretch hundreds of kilometers across. These scars tell the story of a planet that has faced constant bombardment since the earliest days of the solar system. But Mercury is not only a place of destruction. Beneath its battered surface lies a clue that makes it even more fascinating. Scientists discovered that Mercury has a massive iron core much larger, in proportion, than Earth's. This dense heart gives Mercury a surprising strength, a magnetic field. Weak, yes, but still present. And it plays a vital role in shaping how the planet interacts with the sun. Without it, Mercury's strange tail would not exist at all. Despite all this, Mercury remains one of the least explored planets. We know more about Mars, Saturn's moons, even Pluto, than we do about Mercury. Part of the reason is simple. It's very hard to reach. To orbit Mercury, a spacecraft must fight against the sun's powerful gravity. Any mission requires enormous amounts of energy and carefully planned flybys to slow down. Only 2 missions have ever succeeded. The first was Mariner 10 in the 1970s. The second was Messenger, which orbited Mercury between 2011 and 2015. Each gave us new insights, but left even more questions behind. And this is what makes Mercury so mysterious. It is right next door in cosmic terms, yet still feels like a stranger. We see it in the morning or evening sky, but few people realize how extreme it really is. Even fewer know about its strange, comet-like tail. That story begins with the very conditions we just described: the heat, the radiation, the bombardment, and the fragile exosphere. Imagine standing on Mercury's surface. The sun would look more than twice as large as it does from Earth. The light would be blinding, the shadows sharp and black. The ground would be cracked and scorched, marked by endless craters. No air to breathe, no wind to carry sound, just silence, heat, and radiation. And yet, in this silence, invisible forces are at work, lifting particles from the surface, pushing them into space, and shaping them into a glowing trail millions of kilometers long. When scientists first detected this tail, it changed the way we thought about Mercury. Suddenly, it wasn't just a hot, barren rock. It was a dynamic world, constantly interacting with its star, constantly reshaping its space environment. The smallest planet had become a laboratory for studying some of the most powerful forces in the solar system. This is why Mercury deserves more attention. It challenges our assumptions. It shows us how extreme a planet can be, and how much we still have to learn. As we continue through this series, we'll uncover the secrets of Mercury's mysterious tail, the Doppler effect that helped us see it, and the missions that may soon rewrite our understanding of this strange world. For now, remember this: Mercury may be small, but it is the most extreme planet in the solar system, and its greatest mystery is only beginning to reveal itself. Chapter 2: The Tail of Mercury. The smallest planet in our solar system hides one of the strangest secrets. From a distance, Mercury looks like nothing more than a burnt, airless rock circling close to the Sun. But hidden in that blazing orbit is something unexpected. Something that makes this little planet seem more like a comet than a world. Mercury has a tail, a stream of glowing particles that stretches millions of kilometers into space. When scientists first made this discovery, it was almost by accident. Astronomers observing Mercury with sensitive instruments noticed faint emissions in the sodium wavelength of light. At first, it didn't make sense. Why would Mercury, a rocky planet without a thick atmosphere, glow with sodium? The more carefully they observed, the clearer it became. Mercury was releasing sodium atoms, and sunlight was pushing them away from the planet, creating a thin but vast tail. This was unlike anything seen before. We are used to thinking of comets as icy wanderers. They grow tails when they approach the sun, as solar radiation heats their ice and releases gas and dust. But Mercury is not a comet. It is a planet with no ices, no long elliptical orbit, and no fuzzy appearance. Yet, in certain ways, its sodium tail resembles the glowing stream of a comet, long, delicate, and invisible without the right instruments. To understand how Mercury creates this strange phenomenon, we have to go back to the planet's surface. Mercury is bombarded constantly. Solar radiation, solar wind particles, and even micrometeoroids strike its crust. With no thick atmosphere to shield it, Mercury's surface absorbs every impact. These impacts shake loose atoms from the uppermost layer of rock, especially sodium atoms. Once freed, these sodium atoms hover just above the surface, forming a thin, temporary exosphere. An exosphere is not a true atmosphere. It is not thick, it is not breathable, and it does not trap heat. Instead, it is more like a ghostly veil of individual atoms. Each atom moves independently, bouncing away into space if it gains enough energy. Mercury's exosphere is fragile, constantly being stripped and rebuilt. And it is from this exosphere that the planet's mysterious tail is born. Here's how. The sun's powerful radiation interacts with these sodium atoms. When sunlight strikes sodium, the atoms absorb energy. This energy boosts them into a glowing state, making them visible at a specific wavelength of yellow-orange light, the same color that gives street lamps their glow on Earth. But the sun does more than light them up. Solar radiation pressure also pushes on the sodium atoms, nudging them away from Mercury and sweeping them into space. Over time, these particles gather into a long stream trailing behind the planet. The result, Mercury's sodium tail. This tail is enormous. Measurements suggest it can stretch for millions of kilometers, extending far beyond Mercury's orbit. If our eyes were sensitive to the sodium glow, the tail would dwarf the planet itself, appearing like a fiery ribbon pulled across the solar wind. But because the glow is faint and exists in a narrow part of the spectrum, human eyes cannot see it. Specialized telescopes, equipped with filters tuned to sodium's unique light, are required to detect it. In some ways, this makes Mercury's tail even more fascinating. It is a feature that exists in plain sight, yet hidden. Night after night, Mercury circles the Sun, dragging a comet-like tail behind it, and almost no one can see it. Only scientists with the right instruments can reveal it, making it a cosmic secret veiled by the limits of human vision. The discovery of Mercury's tail changed how we think about small rocky worlds. It reminded scientists that planets are not static. Even worlds without thick atmospheres are still dynamic, constantly interacting with the Sun and their environment. For Mercury, the sodium tail is a direct record of that interaction. Every particle in the tail tells a story about how solar radiation, meteoroid impacts, and surface chemistry shape the planet. Comparisons to comets are natural, but the origin of Mercury's tail is entirely different. A comet's tail comes from frozen water and gases boiling away. Mercury's comes from sunlight and bombardment, knocking particles off its crust. One is icy and temporary, the other is rocky and constant. The similarity is only in appearance, a thin glowing trail cast into space by the power of the Sun. As research continues, scientists use Mercury's sodium tail as a probe. By studying its brightness, shape, and changes over time, astronomers learn about the conditions on the planet's surface and the strength of solar radiation at Mercury's orbit. For example, the brightness of the tail can vary with solar activity. During strong solar storms, more sodium is ejected, and the tail becomes brighter. These changes give researchers a way to measure the invisible forces shaping the smallest planet. The scale is staggering. Imagine Mercury, only slightly larger than our Moon, dragging behind it a tail longer than the distance between Earth and the Moon. Imagine this delicate stream glowing faintly in sodium light, invisible to us, yet stretching across millions of kilometers of space. This is not the kind of thing we expect from a small rocky planet. And yet, it is real, a reminder that even the simplest looking worlds hide extraordinary surprises. Why should this matter to us? Because Mercury's tail is not just a curiosity. It is a natural experiment, showing us what happens when a rocky surface is exposed to the raw power of the Sun. It helps scientists understand not only Mercury, but also the processes that might shape exoplanets orbiting close to other stars. If sodium tails exist around Mercury, could they exist around other hot, rocky worlds across the galaxy? If so, then telescopes might detect them, giving us a way to identify planets orbiting faraway stars. This is why Mercury's tail continues to inspire. It blends mystery and science in a way that feels almost poetic. The smallest planet, the one closest to the Sun, wears a hidden crown of light that stretches endlessly into space, invisible to us, yet undeniably there, a feature that makes Mercury feel less like a dead rock and more like a world still in motion. And so, the next time you hear the word Mercury, don't just think of a scorched planet racing around the Sun. Think of the hidden tail it drags through the void, a trail of glowing sodium, carved by sunlight, stretching across millions of kilometers, the smallest planet, with a secret that makes it look, in some ways, like a comet. Chapter 3: The Doppler Effect and Discovery. When scientists first noticed Mercury's strange sodium glow, the next challenge was proving what it really was. They needed more than just a faint signal. They needed to know where the sodium atoms were going, how they were moving, and what that meant for the smallest planet. To unlock the mystery, they turned to one of the most powerful tools in modern astronomy, the Doppler effect. Most of us are already familiar with the Doppler effect in everyday life. Imagine standing on a street corner as an ambulance races past. The siren sounds higher in pitch as it approaches, and then lower in pitch as it speeds away. Nothing about the siren itself changes. What changes is the sound wave reaching your ears. When the source of the sound is moving toward you, the waves are compressed, creating a higher pitch. When it moves away, the waves stretch out, producing a lower pitch. That simple shift in frequency is the Doppler effect. Now, what happens with sound also happens with light. Light, like sound, travels in waves. When the source of light moves toward us, its waves get compressed, shifting toward the blue end of the spectrum. When it moves away, the waves stretch out, shifting toward the red end. This is called Doppler shift. For astronomers, it's one of the most important ways to measure motion in space. From galaxies racing away across the universe to tiny atoms drifting above a planet, the Doppler effect allows us to see movement where our eyes cannot. For Mercury's mysterious tail, this principle was the key. The sodium atoms in the tail emit light at a very specific wavelength, a golden yellow glow, the same color you might recognize from sodium street lamps on Earth. In the lab, this wavelength is constant. But in space, if those sodium atoms are moving, their light will shift slightly toward red or blue, depending on their direction. By measuring these shifts, astronomers can tell how fast and in which direction the atoms are traveling. This technique is called Doppler spectroscopy. It requires precision instruments attached to telescopes. Using narrow filters tuned to sodium's exact wavelength, astronomers can separate Mercury's faint sodium light from the overwhelming glare of the sun. Then, by analyzing the shifts in that light, they can map the speed and motion of the tail's atoms. It is like turning a cosmic glow into a story of movement. The results were stunning. The data confirmed that Mercury's sodium glow was not just a local haze around the planet. It extended far behind Mercury, forming a vast tail that streamed away in the opposite direction of the sun. The Doppler shifts showed that the sodium atoms were not standing still. They were flowing, accelerating under the push of solar radiation, creating a dynamic trail of light across space. This discovery was more than just confirmation. It gave scientists a way to study the structure of the tail in detail. Different parts of the tail showed different velocities. Some atoms moved slowly, clinging near Mercury. Others were pushed rapidly away, stretching millions of kilometers into the void. The Doppler data revealed layers, patterns, and flows, painting a picture of the tail, not as a static feature, but as a living, changing phenomenon. And then came the surprises. As astronomers monitored Mercury's sodium tail over time, they noticed fluctuations. Some nights, the tail glowed brighter. Other times, it seemed thinner, more diffuse. In certain observations, the Doppler shifts revealed unexpected bursts of fast-moving atoms, as if Mercury had suddenly released a pulse of sodium into space. The source of these variations was not always clear. Sometimes they correlated with solar storms, blasts of charged particles from the sun striking Mercury's surface. At other times, they seemed tied to tiny meteoroids colliding with the planet. And in still other cases, the changes had no obvious cause at all. This was perhaps the greatest revelation. Mercury, once thought of as a static, dead world, turned out to be surprisingly active. Its surface is constantly bombarded, and its sodium tail is constantly shifting in response. To detect these changes, scientists rely on Doppler spectroscopy, watching as the wavelengths shift night after night. Each changing color tells a story about the smallest planet's struggle against the immense forces of the sun. It's worth pausing here to appreciate the scale of the achievement. From Earth, Mercury never rises high in the night sky. It is always close to the sun, lost in glare. To detect its faint sodium glow, astronomers must use the most sensitive instruments, and yet, by studying shifts in a single spectral line, they have uncovered a planetary phenomenon stretching millions of kilometers into space. It is a reminder of how much science can reveal, even from signals almost invisible to the human eye. The Doppler effect not only confirmed the existence of Mercury's tail, but also gave us the ability to map its heartbeat. Each observation is like taking the planet's pulse. When solar radiation intensifies, the tail brightens. When meteoroids strike, the tail surges. When conditions calm, the sodium glow fades. It is as if Mercury is constantly whispering, and Doppler spectroscopy allows us to listen. There is also a deeper mystery here. Some of the fluctuations detected by Doppler shifts do not follow predictable patterns. At times, the tail brightens unexpectedly, with bursts of fast-moving sodium that cannot be easily explained. Are there hidden processes within Mercury's crust releasing atoms more efficiently? Are we seeing the subtle influence of magnetic fields? Or is the Sun itself sending out small-scale bursts of energy that trigger these sudden changes? The answers remain uncertain, keeping Mercury's sodium tail a subject of ongoing research. For the public, the idea of Doppler shifts may seem abstract, but the concept is simple. Just as we can hear a passing siren change pitch, astronomers can hear the motion of Mercury's atoms by watching the color of their light change. That small shift reveals vast structures, a comet-like tail attached to a planet we once thought we knew. What began as a faint glow has become a window into the invisible dynamics of the solar system. In the bigger picture, this discovery has implications beyond Mercury. Doppler spectroscopy is one of the same tools astronomers use to detect planets around other stars. If we can detect the faint sodium glow of Mercury's tail from Earth, then perhaps, one day, we can detect similar tails around exoplanets orbiting close to their suns. These glowing trails could serve as signposts of rocky worlds far beyond our solar system, worlds stripped by radiation yet still leaving their marks in light. So the story of Mercury's tail is not just about one planet. It is about the tools of science and the secrets they uncover. It is about how something invisible to our eyes becomes visible through the language of wavelengths. And it is about how even the smallest, most overlooked planet can surprise us with phenomena that defy expectations. The smallest planet, a hidden tail, a trail of sodium atoms, revealed only through the Doppler shift of light. Each discovery pushes the mystery further. What else is Mercury hiding? How many more secrets remain unseen, waiting for the right instruments and the right questions to bring them to light? Chapter 4. Missions that uncovered the truth for centuries. Mercury was one of the least understood planets in the solar system. Its closeness to the Sun made it hard to observe. Telescopes revealed only a shimmering dot, often swallowed by the Sun's glare. Many thought Mercury was just a dead, airless rock, simple, unchanging, and silent. But spacecraft changed that picture forever. Step by step, mission by mission, we began to see Mercury not as a forgotten world, but as a place filled with mystery. And one of the biggest revelations came in the form of its invisible tail. Mariner 10. The first encounter, the first real look at Mercury came from Mariner 10, a NASA spacecraft launched in 1973. Its journey was bold for its time. No one had ever visited Mercury before. The mission used Venus for a gravity assist. The first time such a maneuver was attempted to slingshot Mariner toward the innermost planet. Between 1974 and 1975, it performed 3 flybys, capturing the first close-up images of Mercury's battered surface. What Mariner 10 found shocked scientists. Instead of a lifeless desert, Mercury showed signs of a complex history. Its surface was scarred by craters, but also by cliffs that stretched hundreds of kilometers, evidence of the planet shrinking as it cooled. Most surprising of all, Mariner detected something no one expected, a magnetic field, tiny compared to Earth's, but still there. This was strange, because such a small planet should have cooled long ago, leaving no molten core to power a magnetic field. Already, Mercury was breaking the rules. During those flybys, Mariner 10 also hinted at something even stranger. A thin envelope of particles surrounding the planet. It wasn't a true atmosphere, but rather an exosphere, a wisp of atoms, too thin to breathe but thick enough to detect. Scientists noticed sodium and other elements slowly drifting away from Mercury's surface. Though faint and hard to study, this exosphere was the first clue that Mercury was not as static as once thought. Something dynamic was happening, and the seeds of the sodium tail mystery were planted. Messenger, a decade of discovery. 3 decades later, NASA sent another visitor. Launched in 2004, the Messenger spacecraft arrived at Mercury in 2011 after a long and careful journey involving multiple flybys of Earth, Venus, and Mercury itself. Unlike Mariner, Messenger was designed to orbit the planet. For 4 years, until its mission ended in 2015. Messenger circled Mercury again and again, sending back a flood of data. Messenger's discoveries were groundbreaking. First, it confirmed the presence of Mercury's sodium tail. Instruments on board were able to detect and map the faint glow of sodium atoms streaming behind the planet. What Mariner only hinted at, Messenger revealed in detail. The tail extended millions of kilometers into space, waxing and waning as solar radiation pushed against Mercury's surface. But Messenger went further. It showed that Mercury was geologically active in ways no one predicted. Scientists discovered evidence of past volcanic eruptions, vast lava plains, and strange hollow formations where volatile materials seemed to have boiled away. The planet, far from being a silent rock, had a restless past, and perhaps even processes that continued into the present. Messenger also deepened the mystery of Mercury's magnetic field. It wasn't just weak, it was oddly lopsided, shifted northward rather than centered. This hinted at unusual dynamics deep inside Mercury's core, where molten metal might still be stirring. The connection to the sodium tail became clear. Mercury's magnetic field interacts with the solar wind, channeling particles and shaping how atoms escape into space. The sodium tail, once an odd detail, was now part of a much larger story about how Mercury lives under the sun, as constant assault. When Messenger finally ran out of fuel, it was deliberately guided into Mercury's surface in April 2015. The spacecraft ended its life as a silent crater, but the knowledge it left behind transformed our understanding of the smallest planet. Mercury as a living world. By the time Messenger's mission ended, one conclusion was clear. Mercury was not a frozen relic. It was alive, at least in the sense of planetary activity. Its core still churned, generating a magnetic field. Its surface still released sodium and other particles, feeding a vast tail. It was being bombarded daily by solar wind and meteoroids, constantly reshaped on a microscopic scale. Instead of a dead world, Mercury was revealed as a frontier of planetary science, a place where extreme conditions push matter and energy in unexpected ways. The sodium tail became a symbol of this new vision. It showed Mercury behaving less like a planet and more like a comet, with material streaming away under the sun's radiation. It also showed how little we understood. Why did the tail brighten and fade unpredictably? Why did it sometimes surge with fast-moving atoms? What processes on Mercury's surface and in its thin exosphere controlled this strange phenomenon? These were questions only a new mission could answer. BepiColombo, the next chapter today. That mission is already on its way. BepiColombo, a joint project between the European Space Agency (ESA) and the Japan Aerospace Exploration Agency (JAXA), launched in 2018. It is actually two spacecraft in one, the Mercury Planetary Orbiter, built by ESA, and the Mercury Magnetospheric Orbiter, built by JAXA. Together, they will provide the most detailed study of Mercury ever attempted. BepiColombo has already completed several flybys of Earth, Venus, and Mercury itself, as it spirals inward. Its final arrival at Mercury's orbit is scheduled for December 2025. Once there, the mission will split into two orbiters, each focused on a different goal. The European orbiter will map Mercury's surface and study its thin atmosphere. The Japanese orbiter will explore the planet's magnetic field and how it interacts with the solar wind. For the sodium tail, BepiColombo could be revolutionary. Its instruments are designed to measure Mercury's exosphere with extreme sensitivity, detecting changes over time. By monitoring sodium emissions and Doppler shifts, the mission will track how the tail forms, evolves, and responds to both the Sun and Mercury's magnetic field. Scientists hope to learn not only how the tail works, but also how Mercury's entire system of surface, atmosphere, and magnetosphere fits together. Anticipating surprises, if history is any guide, Mercury will not give up its secrets easily. Mariner 10 surprised us with a magnetic field. Messenger shocked us with volcanic plains, odd hollows, and a sodium tail stretching across space. It is almost certain that BepiColombo will reveal more. Perhaps the tail is more variable than we imagined. Perhaps Mercury's interior is stranger still. Or perhaps the interaction between its magnetic field and the solar wind produces effects we cannot yet predict. That is the beauty of planetary exploration. Each mission answers old questions, but also raises new ones. Mercury's sodium tail, once invisible, is now a beacon of curiosity. It reminds us that even the smallest planet can hold mysteries as deep as any giant world. And it reminds us that science is not just about what we already know, but about what we are still daring to find. When BepiColombo finally arrives, we may have to rewrite our textbooks again. Mercury may surprise us once more, and in doing so, it will continue to reshape our understanding of what a planet can be. Chapter 5: What the tail means for us. When most people hear about Mercury, they think of a small, rocky world orbiting close to the sun, a place too hot, too dry, and too hostile to matter much. For a long time, even scientists thought of Mercury this way. It seemed like the least interesting of the planets, just a lifeless stone circling in the sun's glare. But the discovery of its strange comet-like tail changed that view forever. And while it may sound like a detail too small to care about, the truth is that Mercury's sodium tail has deep meaning, not only for planetary science, but also for our understanding of the universe itself. A window into planetary processes. The first reason Mercury's tail matters is simple. It shows us how planets interact with space around them. Normally, we think of a planet as separate from space, with a clear surface dividing one from the other. But Mercury blurs that boundary. Atoms from its surface are constantly being knocked into space by solar radiation. These atoms are then shaped into a vast tail, invisible to our eyes, but stretching millions of kilometers behind the planet. This interaction is not just an oddity. It is a demonstration of how powerful forces like solar wind and radiation pressure can sculpt an entire world. Mercury's surface is not fixed and silent. It is in constant dialogue with the space around it. That lesson extends beyond Mercury. It tells us that no planet is truly isolated. Every planet, even Earth, is shaped by the energy flowing from its star. Studying Mercury's tail allows scientists to see those interactions happening in real time. The solar wind's fingerprint. Another reason Mercury's tail matters is that it helps us understand the solar wind. The solar wind is a stream of charged particles that flows outward from the sun at incredible speeds. It can strip atmospheres, disturb magnetic fields, and even affect technology on Earth. But its full impact on planets is still not fully understood. Mercury is the perfect laboratory for studying this. With almost no atmosphere and only a thin exosphere, Mercury offers little protection. The solar wind slams directly into its surface and magnetic field. The sodium tail that streams behind Mercury is like a glowing fingerprint of this process. By studying how the tail brightens, fades, and shifts, scientists can watch the solar wind at work. Each change in the tail reflects a change in the invisible forces pouring out of the sun. This has practical value. The more we understand solar wind interactions at Mercury, the better we can predict and prepare for space weather at Earth. Our satellites, astronauts, and even power grids are vulnerable to the same forces. Mercury's struggles with the sun are, in a way, lessons for us too. Mercury as a model for exoplanets. The mystery grows when we look beyond our solar system. Today, astronomers have discovered thousands of exoplanets, worlds orbiting other stars. Many of these planets are extremely close to their suns, even closer than Mercury is to ours. They are blasted by radiation and stellar winds far more intense than what Mercury experiences. Some of them are rocky. Some may even have thin atmospheres or Here is where Mercury becomes important. Its sodium tail offers a small-scale example of what might be happening to those distant worlds. If such a small, airless planet can produce a massive tail, what about exoplanets orbiting mere millions of kilometers from their stars? They could be shedding material into space at rates far higher than Mercury. Those tails might even be detectable with future telescopes, giving us a way to study alien planets indirectly. In this sense, Mercury acts as a bridge between our own solar system and the universe beyond. It is not just about one planet's quirks. It is about using Mercury as a natural laboratory to imagine the strange and extreme worlds scattered across the galaxy, a reminder of hidden mysteries. But there is also something more personal about Mercury's tail. It reminds us that even in our own solar system, a place we thought we knew, there are still surprises. For centuries, Mercury was dismissed as barren and unremarkable. Then came Mariner, Messenger, and now BepiColombo, each peeling back another layer of mystery. A magnetic field where none should exist. Evidence of past volcanism. A comet-like tail no one expected. This tells us something profound. The solar system is not finished revealing its secrets. There may be other strange processes happening on other quiet worlds. The Moon, Mars, even the moons of the outer planets, all could hide features that challenge our assumptions. Mercury's tail is proof that no world is too small, too airless, or too close to its star to surprise us. Lessons in wonder. Finally, Mercury's tail matters because it sparks wonder. Science is not only about data and measurements. It is also about the sense of awe that comes when we discover something we never imagined. Who would have guessed that the smallest planet, the one closest to the Sun, would behave more like a comet than a world? Who would have thought that a planet we once overlooked would become a key to unlocking the behavior of stars and exoplanets? That is the magic of exploration. Every time we think we have the answers, nature reveals a new mystery. Mercury's sodium tail is not just a scientific detail. It is a story of how even the most unlikely places can transform our understanding of the cosmos. So, what does Mercury's tail mean for us? It means that planets are not static. They are dynamic and alive with interaction. It means that the solar wind is not a distant phenomenon. It is a force that sculpts worlds and may one day threaten our technology and lives. It means that exoplanets, scattered around distant stars, might carry their own mysterious tales, waiting to be discovered. And above all, it means that the solar system, far from being fully mapped and explained, is still a frontier of wonder. Every time we think we understand Mercury, it reveals something new, and its mysterious tale may be just the beginning. If you found this exploration of Mercury's mysterious tale as fascinating as we did, consider subscribing for more deep dives into the hidden mysteries of space. Don't forget to like the video and share your thoughts in the comments. What do you think BepiColombo will discover when it finally reaches Mercury?